Hi, thanks for tuning in. This is Scott with the Crescent Method. Today we're going to go over some Logan Lab results from a YouTube subscriber of the channel that followed the instructions for our mock mix on our soil testing procedures, made their own mock mix of soil making materials, sent them into Logan Labs, and got them tested. And so now we're just trying to look through the data to determine which direction we should go and what amendments we need to add to this mock mix when it's a final cubic yard so that we can end up with more desirable targets under those values. And so here first we've got the Mehlich 3 test, and if you start from the top down, it does have the sample depth noted as 4 inches. And if you have a bulk density value, then this doesn't matter. But if you don't have a bulk density value, this is actually one of the most important aspects of the soil test, because to calculate ppms of concentration of nutrients, or pounds per acre for that matter, it's a consideration taking the weight of the soil and the weight of the grams of element in that soil to determine concentration in parts per million. So most of the soil testing labs are assuming that you're taking soil from native soil, from the ground, that has a weight of 2 million pounds when they do what they call a 6-inch acre slice. So when you take 1 acre, slice off 6 inches, supposedly that weighs 2 million pounds. I rarely see a soil in my mineral recommendation inbox that has a soil that actually weighs 2 million pounds. So for any potting mix, cannabis-based situations, absolutely imperative that you have the bulk density value from my perspective. So that's what that means. Going down, we've got the exchange capacity, which is 14.85, which takes into consideration the values for calcium, magnesium, potassium, and sodium, and puts them into a formula to spit out that exchange capacity value. There's a video on the channel that covers that math. I use the exchange capacity value as an interpretation of the total nutrient pool in the soil on the Mehlich 3 test. And for cannabis and for a potting soil, we really want to see this number above at least 15 to 18, more desirably something like a 20, 23, 25. And so at a 14, we don't quite have enough nutrients to get a good outcome from my assessment. The pH of this particular sample is 7.1, and that's mostly because calcium, magnesium, potassium, and sodium are not quite in balance. As we start to correct those values, the pH will change on following soil tests. I personally never take a strategy to purposely drive up or drive down pH. I personally only take a strategy to balance the nutrients, and pretty much every time the pH starts to correct into a more desirable fashion. Again, though, I'm a biology guy. I'm diehard soil food web, and I believe that the organisms on the root system of a plant are driving pH at a much smaller level than the soil test can analyze. Nonetheless, the next value is organic matter of 14.71. Typically, we like to see this number at like 20 or 30%. So I would consider figuring out how to get more organic matter in that soil test. And next we have sulfur and phosphorus. Sulfur is at 99 parts per million. Phosphorus is at 308 rather. And most people try to get sulfur, phosphorus, and potassium towards each other. And the textbook would say maybe sulfur should be half of potassium or half of phosphorus. For cannabis, we're trying to get them all close together. So I would say increase sulfur by 1 to 200 parts per million. We're going to increase that phosphorus by another 100, 150 parts per million. And then moving down to calcium, magnesium, and potassium, just from past experience, I feel that calcium has to be at least 2,000 parts per million. When you start to get calcium, magnesium, and potassium in balance, and calcium is about 20%, 2,000 parts per million, you're going to have about a 20 on the exchange capacity, just the way the numbers work out. So our first goal is going to be to increase calcium and see how that plays with the magnesium and potassium values on the test. The next line down, the dark gray bar, is the base saturation values, which I think on this soil test are some of the most important numbers, because it's taking into consideration how much of the soil particle is occupied by a given element. And the ideal soil textbook says that we should have 68% calcium, 12% magnesium, and something like 4% potassium. For a potting soil and for cannabis, that does change. So I'd like to see at least 68% on up to 70, 73%. Some people drive it as high as 80%. Depends on the composition of that soil mix. For this exercise, we're really just trying to get calcium to 68% or so. Magnesium, we want to see 10 to 14%. And potassium for cannabis in a potting soil, you really can run it anywhere from 4 to 8 and as high as 10% maybe. But for this exercise, we're going to try and get 68 to 70% calcium and see what happens to magnesium and potassium. This is the AA 8.2 test, which was gathered by the YouTube subscriber. And I don't particularly use the AA 8.2 test very often, or really at all, honestly. In my own personal research of talking to the various lab directors, asking when this is appropriate and when this is not appropriate, most of them seem to feel that this test doesn't really provide you any added value until calcium is 5,000 parts per million or more. In this situation, we have 1,700 parts per million. That's a long ways from 5,000 parts per million. In this situation, the person thought that because pH was above 7, it would be an advantage. I don't know that that necessarily applies in this situation. I'm not sure if that's common thought elsewhere in the industry. I don't personally execute it this way. But it's interesting to see how the values are different. So instead of 1,700, we have 711 parts per million of calcium, which is what this AA 8.2 test is supposed to do. By using a different extraction agent and by increasing the pH to 8.2, it represents or measures the calcium, magnesium, potassium in different ratios. And you can see that reflected in this soil test versus the other soil tests. So whereas we had 57 base saturation on calcium, we got 53, 54 on this 8.2 test. Where we had 21 on the Mehlich 3 for magnesium, we have 17 for this. So it does change the way those data points are represented, which in certain cases that can be valuable. I don't think this is one of those situations though, so we're gonna keep moving. And this also came with a saturated paste test. I believe that the saturated paste test is valuable and I think it is helpful. I just don't personally like to live and die on it. There's a lot of cannabis consultants that really live and die by the saturated paste test, but typically those people are also not incorporating biology in a real functional way. And so because our focus is biologically driven, we can see downstream effects of the biological communities on the saturated paste test. That doesn't mean we just disregard it, but I don't live and die on it. I feel that for living soil and high biological systems, you have to maintain the Mehlich 3 test because that is the total nutrient pool in the soil, while still monitoring the saturated paste test, using that to guide your decisions on the choices of amendments. So in this situation, we have significantly less soluble calcium than we would want. So on a saturated paste test, we want to see more like 60% calcium for this base saturation, which is below the red stripe there, where it says percent. Those values are the base saturation values for this particular saturated paste test, which the math is a little bit different. So in this situation, we want to see 60% calcium, 20% magnesium, and maybe like 12% potassium. So we're way over the target on potassium at 40%. We're way below the calcium target at 17%. But again, as a biology guy, that doesn't scare me too much. We just need to correct the underlying issue, correct the soil, get biology inoculated, and keep it moving. So this is a spreadsheet that I created to do this type of math. It simply takes the math from one of my older videos explaining the various math and just put it into a spreadsheet form. And so these yellow boxes are where I enter data. The gray boxes are where the spreadsheet is reporting data based on the formulas in other cells. And so I've already put the values for calcium, magnesium, potassium, and sodium from our Mehlich 3 soil test. We can see that our exchange capacity is the same as the Logan test at 14.85. And we can see that our base saturation values are similar to that of the Logan soil test. So our spreadsheet is working correctly and we can move forward. This little guy here is a tool that helps me forecast a percentage increase. So 1715 is our calcium value. If I want to increase that by 20, 30, or 40%, that's what the value would be going across the top. Coming down below the number is the amount that number would be increased. So to get to 2058 from 1715, That's a 343 part per million increase. So this just helps me be quick on the math and go to where I need to go with the various tools. We're not going to necessarily use that today, but that's what that is. And then down here is a percent increase calculator, which helps me put a low value and a high value and figure out the percentage increase as well as the numerical difference. So again, I can save a step on my math. I'm not a big fan of all-in-one magical calculators for soil testing. I think that way more needs to be left up to the discretion of the person doing the math. I find a lot of problems with magical all-in-one calculators that just spit out a result. I think it needs a lot more specific critical thinking. And honestly, if you just have a tool that does the math for you, you don't need one of those magical tools. So we're going to start plugging in some numbers and see what we can do. So, right, our goal is, can we get base saturation values closer to 68% calcium, 12% magnesium, and 4 to 9% potassium? So we're going to come up to our calcium level. We're going to increase it to 1800. That brings to 58. That's not near enough. Let's try 2000. 2000 gets us to 61% base saturation. And as you can see, the magnesium and potassium are both dropping because we are occupying more of that soil particle with calcium. That's still not enough. So we're going to maybe, I don't know, 2200. Let's try 2200. Not enough. Maybe 2500. That's getting us closer. Maybe 2800. So 2800 gets us to 68% calcium, 15.2% magnesium, and 10.3% potassium. I think that's a pretty good place to start. So we'll just kind of work with that. So now we're going to go to our percentage increase calculator, and we're going to put 2800 for the high value, and we're going to put 1715 for the low value. And we end up with a difference of 1085. And so what I do is I come down to this guy right here now, and we're going to increase calcium by 1085. So because magnesium and potassium are already too high from a base saturation consideration, and because there's plenty of soluble magnesium and potassium on the saturated paste test, we're going to leave magnesium and potassium alone, and we're going to move on to sulfur. And so sulfur on the test is about 99. We want to try and get this up to the phosphorus and bringing it closer to the potassium value. So I don't know, let's say not to exceed 200 parts per million maybe for sulfur. And phosphorus is at 300. If we're going to increase sulfur, and potassium is already high, cannabis loves to gobble down phosphorus, we're going to put some more phosphorus in there. So let's say maybe 150 parts per million to be conservative and just find a basic starting point. So from a very basic consideration, just for balancing the nutrients on this mock mix for his compost source, for his aeration source, for his cocoa and peat mix, or whatever he ended up using there, this is the minerality that's left of it. And in order to balance those components, we need to add roughly another 1100 parts per million of calcium. And then we're just going to want to increase sulfur and phosphorus along with that. So it's just a very basic consideration. Now, this doesn't take into consideration other aspects of the soil mix, like should there be clay in there? I would say yes. You know, should there be other things that aren't just specifically CalMag, potassium, sulfur, and phosphorus? For sure. But we're trying to just keep the math simple and start with the really basic considerations. So now, if we go to our AA 8.2 test, just for fun, we can punch these numbers into our spreadsheet and see how that pans out. So 711, 140, 523. Our sodium's different, and our other bases and exchangeable hydrogen stays the same. So now that our spreadsheet has the correct data for the AA 8.2 test, let's now start tinkering around. So let's jump to 900. That brings us to 60, not enough. 1,000, 61, not near enough. 1,400 maybe. Okay, so now we're getting closer. We're at 68.4, 11.4, and 13.1 on our base saturation side. You know, let's go in the right direction. Maybe we go a little bit more on the calcium. Maybe we go a little bit more. So let's say 1,500. So we go over to our high value, low value calculator. And it was, back up here, 711. 711. So 711 for our low value. And we're going to want to increase calcium by 789. So now we come down here, put in our little notes so we don't forget. And we're going to leave magnesium and potassium at 0. And because sulfur and phosphorus stay the same on the 8.2 test, we're going to just keep those same targets for simplicity. So now we move over to our next page, which does the calculations for grams of element contributed by a given compound. And our numbers are carried over from the test mostly. 789, 0, 0, 200, and 150. Okay, so our bulk density on our Mehlich 3 test is 0.32, so we're always going to anchor our soil weight, because again, it's a weight by weight comparison. We're anchoring our soil weight with our bulk density of 0.32, which converts to a soil weight in kilograms per cubic yards of 245 kilograms. And we're looking to increase 1,085. So let's try 1,085. And let's go to our mineral content calculator for calcium. And we know we need soluble forms of calcium, so we can do this ag lime, which is micronized, or we can do gypsum. We're not going to do dolomite because that is magnesium, and it's just generally a bad choice. Oyster shell is fine, but it's not soluble. So because we could use some sulfur, we're going to use our gypsum. So that's 22% calcium, 16% sulfur. So we represent that as a decimal, and amendment analysis 1 and 2 is for our calcium and our sulfur. And it says there that we're going to need 1,208 grams of gypsum. But if you look down here, this is where the ppm contribution of the given element is reported. And so for calcium, we're going to get 1,085, which is what we want, but we're getting darn near 800 parts per million of sulfur, which is just way too much. So we're not going to be able to do that. So if we're trying to keep sulfur below 200 parts per million and we're contributing roughly 800, we can divide that by 4. So if we do 1085 divided by 4, that gives us 271. So we come up here and start again. I'm going to go 271 parts per million is our new goal. There you go. So now 301 grams of gypsum contributes 271 parts per million of calcium, 197 parts per million of sulfur. So we're going to go ahead and note that. And we're going to do 301 grams gypsum. And we can see that if we come down to this lower calculator, we can check our work and we can see that 302 grams of gypsum at 16% sulfur gives us 197 parts per million. So we're also going to come down here and write 197 ppms from gypsum so we don't lose track and we don't double up something that we're already inheriting. But the problem is we got 271 and 1085. So we need another 814 parts per million. 814 parts per million, right? Yep. We need 814 parts per million in another form of calcium. So we could use agricultural lime. We could use oyster shell. For simplicity, we'll do oyster shell. People are pretty familiar with that. So that has a 36% calcium value. So we represent that as a decimal because that's the way the math works. And we can see that at 814 ppms with oyster shell that has a 36% analysis, we're going to need 554 grams essentially. And that gives us our 814. So write that in our notes. So 514 oyster shell flour. So pretty straightforward there. So we've got our calcium handled, we've got our sulfur handled, and next we need to move to phosphorus. So if we want to get 150 parts per million of phosphorus, we need to figure out what we have available. And there's not a lot of good options of just phosphorus. So you can use other things, obviously. So we could do fishbone if we wanted, but we'd have to calculate for the calcium as well, and that's a little overly complicated for this current example. We could use fish meal, same thing, but they all have multiple values. And so just for the sake of this exercise, we're going to look at CalPhos, which is 3% phosphorus. And it also has a calcium, but the textbooks and the people say you don't factor in the calcium of the CalPhos. So we're just going to look at the 3% phosphorus. We'll go back to our amendment. We're going to represent that as a decimal, so the math works. And to get 150 parts per million on a soil that weighs 245 kilograms per cubic yard, we need 1,224.76 grams of CalPhos. So we'll just call it 1,225. So if we go 1,225 grams CalPhos, now we've handled our calcium, magnesium, potassium, sulfur, phosphorus values. So this soil test doesn't have a nitrogen on it, or else I would correct the nitrogen. Normally that comes with this test. Sometimes there's just values missing for whatever reason. But yeah, it's a pretty good little exercise right there. So now if we want to go to the AA 8.2, we're trying to get 789 grams. So we've learned from our previous example that we can't do it all with gypsum. So one can assume that we're also going to use 300 grams of gypsum. And then now we got to figure out the oyster shell. So 301 grams gives us 270, and we're trying to get 789. 270 and 789. So we need 519. So we need 519 more parts per million of calcium using a 36% oyster shell flour. That's 353 grams of element. So, if we scroll down to our little notes here, based on the Mehlich 3 test, we're going to want 301 grams of gypsum and 514 grams of oyster shell per cubic yard. If we believe that the 8.2 values are correct, which I don't, but if we did, we would then use 301 grams gypsum and 353 grams of oyster shell. So, there's like a good 40% variation in what you're going to need to correct the soil to hit the target values. So just some things to consider. So that's what I would do there. And, I hope this helped. If there's any other questions, drop them in the comment section, hit the like, and we'll see if we can get you answered. Thanks for tuning in. Bye.